All right, let's get started. So this is the oral session, Gravitational Waves and Multi-Messenger Astronomy 1. I'm Matt Wiesner, and I'm going to be the session chair. So our first talk is by Nathan Lee on the chaotic three-body problem in Newtonian gravity. Now, I encourage you to, if you have questions as the talk goes on, to put them in the Q&A or the chat, and I will be monitoring that. And we'll share those questions with the presenter at the end of the talk. All right, Nathan, it's all yours.
Thanks. So I'm Nathan Lee. I'm faculty at the Universidad de Concepción in Chile. And today I'll be talking about a statistical mechanics-based formalism for the chaotic Newtonian three-body problem. And the work I'll be talking about today was done in collaboration with Nick Stone and Jeremy Webb, and summarizes two papers, one just published last year, and one hopefully to be submitted very soon. So one of the primary interests in the three-body problem today is for making black hole binaries that later merge and are detected via their gravitational wave emission. So how does the dynamical channel work for putting black holes into binaries? Well, the upper left inset shows a typical globular cluster in our galaxy, 47 Tuc. And the collision rates are high in dense stellar environments like globulars, which means binaries and singles very often interact directly. And this is shown in the lower right inset, which is a depiction of a single binary exchange interaction. So the original binary comes in from the left and contains objects 1 and 2, and it interacts directly with the single star that comes in from the right, labeled object 3. A chaotic interaction ensues, and it usually ends with one object being ejected, which is usually the least massive object, in this case, object 2. And so this leaves the most massive objects, in this case, objects 1 and 3, bound in a binary. And you can imagine if object 3 is a black hole, then what this did is it exchanged a black hole into a binary. And so if this happens a second time via a second exchange interaction, then we end up with two black holes in a binary that could later merge due to gravitational wave emission and be detected via gravitational wave observatories. And this is how the dynamical channel works. So the general three-body problem is an example of chaos in nature. And what this means is that small perturbations to the initial state can compound over time and cause deviations in the outcome from realization to realization. So this is often called the butterfly effect and is depicted here for the three-body problem. So three bodies are initially released from rest, and their distances from the system center of mass are plotted as a function of time. Many simulations are performed, each time perturbing the initial state just slightly. And the takeaway message is that the time evolution remains more or less the same as before, but over sufficiently long times, the trajectories of the particles through phase space diverge. And so together with my collaborator, Nick Stone, we've developed a new method to analytically compute the probability for any final end state of the chaotic three-body problem from first principles. So what our method does is it maps an initial set of conditions, shown on the left, to a distribution of outcomes, shown on the right. And so we predict all of the relevant distribution functions, including the distributions of orbital energies and eccentricities for the leftover binary, as well as the distribution of escaper ejection velocities, and so on. And so I don't have time to go into too many details of our work, so please see our paper for all the useful things that we derive, but I'll focus on one aspect, which is the final distribution of binary orbital eccentricities, which is shown here as a function of the initial orbital eccentricity. And the key point is that in the limit of low angular momentum, we find suprathermal eccentricity distributions. So our formalism predicts more eccentric black hole binaries from the dynamical channel than previously predicted. And this should ultimately translate into an enhancement in the rates of black hole binary mergers due to gravitational wave emission, since higher eccentricities translate into shorter gravitational wave merger times. And so why is this formalism so useful? Well, it allows us to evolve entire populations of binary star systems forward through time due to single binary interactions in dense stellar environments, and we can do this purely analytically. So if you consider a population of binary stars all orbiting within a star cluster, this is analogous to a population of binaries in a thermal bath, with heat being transferred from the single stars to the binaries via single binary interactions. And the takeaway point is that this function in the equation I show here, which is a rough description of our Boltzmann equation, the function in bold is what we derive in Stone and Lee, and this is what is needed to plug directly into our Boltzmann equation. So our method provides a technique independent of computational methods, and this is ultimately a game changer for this problem, which is because the addition of binaries makes the computations prohibitively expensive. So because the method is analytic, we can sweep through the parameter space of initial conditions with minimal computational expense. And so just to quickly show some preliminary results of this. So here I show the results of integrating analytically over our Boltzmann equation for a period of 100 relaxation times. Each relaxation time is illustrated via a different colored line, with the initial distribution shown by the black line. And the key point is that our formalism diffuses binaries to more compact states as they become hardened via single binary interactions. So compact binaries in the cluster ultimately become even more compact over time due to this effect. And this is pushing binaries into the regime where gravitational wave emission can take over and drive mergers of black hole binaries. So our method quantifies the rate at which this happens as a function of your initial conditions. And simultaneously, heat is being transferred from the binaries to the single stars, providing a heat source for the cluster, which we are also able to compute the rate of. So we can compute things like the back reaction on the host cluster and the time at which it bounces out of core collapse and goes from falling into a very high central density state to a lower density state mediated by the binaries and the single binaries exchanging energy to the singles and providing a heat source. And very briefly, I'll just show a comparison between our analytic model and the results of n-body simulations, including binaries. So our analytic model is shown via the solid blue line, and the results of our n-body simulations are shown by the black dots here. And we're showing the comparison evaluated after a period of 10 core relaxation times. And this is just to illustrate that so far we're seeing very good agreement between our analytic predictions and the results of n-body simulations. So we're verifying our analytic method using computer simulations. And I'll leave it there. I'll leave up my summary slide and take questions. Thank you very much.
Thank you. Are there questions for Nathan? Let me ask a question. How would your model deal with neutron stars?
So that's an excellent question. So the neutron stars would ultimately be an object of a particular mass. And so that's exactly what we could predict. We could predict the rate of formation of low mass X-ray binaries by computing the rate at which neutron stars are exchanged into binaries via single binary interactions. And in globular clusters, we've known for quite a while that empirically, you do see good agreement between the analytic collision rate and the frequency of low mass X-ray binaries or binaries containing neutron stars. So we know in very dense environments, you have more LMXBs because of these dynamical exchange interactions that ultimately put more neutron stars into binaries than you would get primordially just from star formation alone. So our analytic method you can basically give us any set of initial conditions for any type of star cluster. And after some amount of time, anytime you want, we can tell you exactly how many neutron stars are now in binaries. We can tell you their orbital periods and if they should be emitting in the X-ray, if the orbital periods are short enough for the neutron stars to be accreting from their binary companion. And so we could actually predict an exact number of LMXBs for any set of initial conditions, which is not something you can do with a computer very effectively right now.
Great, thank you. Any other questions?
I'll just leave up an advertisement for a textbook we have coming out called Moving Planets Around. If anybody's teaching celestial mechanics in the near future, please think of using our textbook, available via MIT Press.
All right, so our next talk was withdrawn, and so we actually have a 10-minute break here. And at 11:20, we will have Fabio speaking. So we're going to take a little break. Don't go anywhere. All right, so we're going to start getting ready for our next talk, which will be by Fabio Pacucci. Fabio, if you want to get set up.
Yep, I'm here. Never left. Can start whenever you're ready.
Okay, just a couple more seconds till exactly 10. Oh, there we go.
Yep.
All right, so
All right.
Fabio will be talking about, I'll let you read your title, go ahead.
Hi everyone. Good morning from Cambridge, and it's my pleasure today to briefly introduce you to a model that we recently developed with Avilab, also at the CFA, dealing with separating the accretion and mergers in the cosmic growth of black holes. So I just wanted to start from a fact. We know that black holes come of all sizes. We know that they span a very wide range in masses, about 9 orders of magnitude. So we have stellar mass black holes up to 100 solar masses, and reaching to supermassive black holes approximately from 1 million to 10 billion solar masses. So in order to reach such a large variety of black hole masses, of course, black holes need to grow. So the final goal of our model was to determine the main growth channel, so accretions or mergers, as a function of the black hole mass and as a function of redshift. So unfortunately, I don't have time to go into the details of the model, but I just wanted to give you a very brief idea about how we compute mass growth rate, but please feel free to ask me questions later on or read our paper. So gas accretion is the mass added by accretion is calculated from the quasar luminosity function. So this is an approach very similar to the Sultan argument that is well known. Instead, the mass added by mergers are calculated with a merger tree approach. So I'll go directly to the main result of the paper. I'm going to describe you this plot that has on the horizontal axis here the log of the black hole mass. So from 1,000 to 10 to the 10 solar masses, so very large black holes. And on the vertical axis, you have the redshift. So we go from cosmic time in the local universe, redshift 0, to redshift 10, so approximately the redshift of the farthest galaxies observed so far. So wherever you see blue in this plot, it means that accretion is dominant. So mass added via accretion is dominant over mass added via mergers. Instead, wherever you see red, the opposite is true. So these lines here indicate where the model predicts that the mass added via accretion is equal to the mass added via mergers. So to start with, you can see that the peak of the quasar activity between redshift 2 and 3 is fairly well predicted by our model. We see that black holes are accreting, not much merging, independently on the black hole mass around redshift between 2 and 3. So our model basically predicts that fairly small black holes in the local universe add more mass by accretion than mergers, and very large black holes mostly add mass via mergers instead. In the faraway universe, in the distant universe, the opposite is true. So small black holes mostly add mass via mergers. Instead, large black holes mostly add mass via accretion. So why is this important? Well, of course, because the growth channel determines the way we can observe these sources. So with future space-based observatories, as I'm going to show you right now, we can observe most of this parameter space. Everybody knows here that gravitational waves are very important to probe mergers. So LISA will be able to observe all of this parameter space shaded in blue. And in particular, our model predicts that it will be fundamental to determine this area where many mergers are predicted to occur. Instead, X-rays are very efficient in probing accretion. So future or perspective X-ray missions like these three will be fundamental to probe this part of this parameter space, most of it basically, and will play a crucial role in observing black holes accreting throughout cosmic time. So I just wanted to conclude this very brief presentation talking about another implication of our model, because we know from previous theories that if a black hole mostly adds mass via accretion, then it's expected to have a high spin parameter. Instead, if it mostly adds mass via mergers, the spin parameter is expected to be lower. So our model predicts that small black holes in the local universe have a high spin parameters, just as large black holes in the faraway universe. Instead, large black holes in the local universe and small black holes in the faraway universe are expected to have a lower spin parameter. And we actually tested our model in the local universe. So you see here a redshift lower than 1. The size of the circle here indicates the spin parameter. So the larger the size, the faster the spin the black hole is rotating. And you can see here that going towards a higher black hole masses, the median spin parameter decreased as our model predicts, because we are going to the merger dominated area. So I will just leave you with my summary. I thank you for your attention, and please feel free to ask me some questions. Thank you.
Thank you very much. Are there questions for Fabio? So just a reminder, if you've come in recently and if you have questions, you can use the Q&A button and type your question in there. All right, we have a question from Camille. Do we have enough spin measurements for the local universe to not worry about observational biases for spins?
Yes, that's a very good question. Thank you, Camille. And we tested our model in the local universe with 22 AGNs, for which we have accurate measurements for the spin parameter. And these are the 22 circles that you see here. The difference between the continuous circles and the dashed circles is that these are lower limits. So it means that we can just give a lower bound for the spin. So you are absolutely correct saying that there could be a bias, and these measurements are not extremely precise. But here in the median spin parameter in the upper panel, I showed the calculation of the median both with precise measurements, so point-like measurements, and with dashed measurements, meaning the lower, only lower bound measurements. And both of these groups seem to indicate that going to higher black hole masses, the median spin parameter is decreasing. So we are first looking forward to more measurements of the spin. Measuring the spin, as we know, is very tricky, and because you need to probe very close to the event horizon of the black hole to reach the measurement of the spin. But we are looking forward especially to test our model at higher redshift, because we could go into regions in which the accretion onto the black hole is not as efficient as in low redshift, in the low redshift universe. So it's not obvious that you expect higher spin parameters if accretion is dominant. This has been proved only in the lower redshift universe. So we are very looking forward to have measurements of the spin also at higher redshift to prove or disprove our model.
I have a quick question for you. So when the matter is being accreted by the black holes, what kind of matter is that? Is that mostly hydrogen gas, or?
Yeah, we just assume that it's gas. Yeah, like whatever falls. Because in order to compute the mass at the accretion, we use something similar to resultant argument. So we are saying that we see light coming from quasars at different redshifts. So we can compute a quasar luminosity function at different redshift. And then with some transformation, we can go from a quasar luminosity function to a quasar mass function, going with the net-Hinton ratio distribution that is a function of the redshift and on the black hole mass. And then from the distribution in mass, we can also compute the mass accretion rate onto the black hole. So whatever mass is being accreted, we really don't care in the model, because we are just computing it from the quasar luminosity function of different redshifts that we have available so far.
Thank you very much.
Thank you.
All right, if you could unshare, then we will
Yes.
get ready for the next speaker. All right, our next speaker is Tusif Islam. Tusif, can you hear me? Tusif, are you there?
Yes.
Okay, wonderful. Can you share your screen, please?
Just a moment. Can you see my screen?
I can, if you just hit play on your slides.
Sorry.
If you could just hit we see all your slides right now. So if you could maybe begin slideshow.
This is fine. I'll go with this.
Okay, sounds good. That's all yours.
Okay, thank you. Okay. So hello everyone. I'm Tusif Islam. I'm a PhD student at University of Massachusetts, Dartmouth. So here in this talk, I'll basically summarize a test to distinguish the no-here nature of binary black holes using the consistency of different modes of gravitational wave radiation. To begin with, in general relativity, the gravitational radiation from a binary black hole system that can be uniquely determined by its masses and spins. Now, hence, the multiples of different radiation that have to be consistent with the same values of black hole masses and spins if you measure those from different multiples. Now, that means that the consistency between different modes of observed signal that can give a powerful test that the radiation is produced by a binary black hole system in general relativity. So here we'll propose a test which based on this philosophy. Now to formulate the test, we split the signal in the dominant quadrupole mode, which is the total mode here, the first term, and then the higher order modes. In higher order modes, you have all other modes for L equal to 3, 4, and so on. Now, in the 2-2 mode, we have the intrinsic parameter lambda. Lambda is basically the Charp mass and mass ratio of the system, which gives you a sense of the masses of the two binary black holes. And in the higher modes, instead of apart from having lambda, we also introduce a deviation parameter called del lambda. Now, del lambda is basically consists of two different parameters. One is deviation in the Charp mass, and one is deviation in the mass ratio, denoted in del MC and del Q. Now, in general relativity, if we estimate these parameters, then del MC and del Q should ideally be 0. But for binary black holes, but let's say the gravitational radiation that is coming from compact objects which are not binary black hole in GR, or even the signal is produced by a different underlying theory of gravity. In those cases, your del lambda values would not be consistent with 0, and they will have some non-zero values. So based on that, you can test that whether general relativity is correct, or whether the signal is coming from the binary black hole in general relativity. Now here, to begin with, we consider non-spinning binary black holes. But in later on, we are planning to also include spins in our test. Now, what we do here is that we estimate the posteriors of the distribution of lambda and del lambda, along with all the extrinsic parameters that describe the location and the orientation of the binary black holes using Bayesian parameter estimation setup. Now, and for that, we inject simulated GR signals. We use the realistic 3 detector setup for LIGO Virgo, Hanford, Livingstone, and the one in Virgo. So all signals we inject in our study, they have a signal to noise ratio of 25. And we use 4 different modes here. Apart from the 2-2, you can see 2-1, 3-3, and 4-4. And to do this test, we use one phenomenological waveform model that has been developed by Mehta et al., which is a non-spinning model. And then to test that our results are, it does not depend on a waveform model, we also use the no spinning limit waveform coming from this NR hybrid surrogate waveform model listed in 2. Okay. Now first, we consider 2 different ways to do the test. One is we introduce one deviation parameter at a time. That is, we introduce only del MC, keeping del Q equal to 0. And in other cases, we introduce only del Q and keeping del MC equal to 0. That was one particular way. And then we also estimate both the parameters simultaneously. Now here we show an example of a result for a simulated GR signal coming from a total of 80 solar mass binary system with mass ratio 1/9, inclination 60 degree at a distance of 600 megaparsec. So the total SNR is 25, as said earlier. Now what we show in the right figure is that in the middle panel, we have the 90% and 50% credible interval shown here, and the GR expectation, which is del MC 0, del Q 0, that's shown in a plus sign here. Now, as you can see, this is a GR signal. So the test should able to say that the signal is GR, which it's able to do that because the GR expectation is within the 90% contour. And then we also show the 1 deviation and 2 deviation posteriors in the upper and the lower panel here. And as you can say that the 1 deviation, when you have 1 deviation at a time, then your posteriors are much narrower than when you have 2 deviations simultaneously. Now, here we show that the test, if you have a GR signal, that test can say that the signal is GR. Now we demonstrate that the test can also identify when the signal is sufficiently different from a binary black hole signal in GR. Now to do that, we inject a neutron star binary black hole waveform coming from numerical relativity, but we rescale the waveform to a solar mass of 120 to total mass of 120 solar mass and mass ratio 1/6. This total signal to noise ratio for the system is 50. Now this means that total mass of 120 and Q 1/6 means the neutron star has a mass of 70 solar mass, but that is okay because here we are treating the rescaled NSBH waveform as a proxy of a signal that comes from a non-binary black hole compact objects in general relativity. We are not treating it as a neutron star binary black hole. And the idea is to see whether when you inject a non-binary black hole signal in GR, whether the test can differentiate that or not. Now, in the right, we show the waveforms here for the rescaled neutron stars, and also here we show the posteriors that has been inferred And in the contours in the middle panel, you can see the black basically shows the contour that is recovered from the rescaled NSBH waveform. And the GR expectation, that is 0, 0, denoted by the plus sign, that lies outside 90%. That means that the test is able to distinguish that this is not a signal that comes from binary black hole in general relativity. Along with that, we also show the posteriors that has been recovered from a binary black hole system in orange, and the binary black hole system has all the parameters consistent with the NSBH waveform. The only difference is it's a binary black hole. And for that particular system, the GR expectation 0, 0 that lies within the 90% credible interval, showing that the test is able to say that this is GR signal, and the other one shown in the black, that is not a GR signal. And finally, we did a study on the uncertainties of the deviation parameters del Q and del MC for different total masses, different mass ratios, and different inclination angles, ranging from inclination angle 30 to 90, mass ratio 1 to 9, and total mass 40 to 200. So, and what we have found that for large mass ratios, that's been Q less than 1/2, and high inclination angles, that is iota greater than 60 degree. This will allow precision test because the del MC and del Q, the 90% credible interval falls below 10 to the power minus 2 and 10 to the power minus 3, indicating that with real data, you can do this test. And for these kind of systems, you can able to say whether the signal is coming from a binary black hole in GR or not very accurately. And finally, I'll stop with this slide here to do so here we do a crude population study, and we use two different power laws used by LIGO for the binary black hole populations for M1 and M2, and we find that almost 20 to 40% of the detectable binaries will have a mass ratio that is smaller than 1/2, which is when we get the better accuracy, and out of which 15% would be observed with inclination angle greater than 60 degree. So thus, this means that only a few percent of the observed signals are likely to have large mass ratios, which suited for our test. But given that LIGO Virgo is detecting hundreds of binary black holes over the next couple of years, we would have enough number of systems where one can do this test and find interesting results. And with this, right, I'll stop here. So if there is any question, I'll take that.
All right, thank you. So we're a little bit behind time, so we're going to go right on to the next talk. Thank you very much for that talk. If you would please stop sharing screen.
Yeah, sure. Okay, thanks.
All right, our next talk will be by Brendan O'Brien. So if you would share your talk, please.
Okay, hopefully you can hear me and see my screen okay?
Yes,
great.
We can hear you. It's all yours.
Awesome, thanks. So good morning, everyone. My name is Brendan O'Brien, and I'm presenting the Search for Intermediate Mass Binary Black Holes on behalf of the LIGO Virgo Scientific Collaboration. So just as a reminder, IMBHs are a missing link between stellar mass black holes, which have masses ranging up to 100 solar masses, and supermassive black holes, which can have mass greater than 10 to the 6 solar masses. Now, although there's strong observational evidence to support both of these two classes, the same can't be said for IMBHs. There has been some indirect evidence for the existence of IMBHs, but none yet have been conclusive. Now, despite that, the astrophysical origin has been studied extensively, and as we heard from a few talks ago, there's mainly two proposed channels for this mass regime, namely hierarchical mergers and accretion onto stellar mass black holes. Now, with LIGO, we search for IMBH binaries, which we define as a binary black hole system which contains either an IMBH component or an IMBH remnant. In other words, we're looking for systems with total mass greater than 100 solar masses. Now, as a general rule of thumb, a binary black hole system with a high mass will emit gravitational waves at a low frequency. And in the case of LIGO, when the total mass enters the INBH regime, you begin to fight against the low frequency seismic noise of the detector. So on the right, I have plotted frequency, on the y-axis is strain, and you can see as you increase the total mass of the system, again, the frequency of the emitted gravitational wave is lower. You end up fighting against this wall of seismic noise. Now, as a result, any INBH signal found in the LIGO detectors will be short in duration and lack the characteristic chirping up shape, which usually describes the GW detections by LIGO. So the summary of all of this is that, in general, INBHs can be difficult to detect in LIGO band. Now, with LIGO, we employ two approaches for the search of INBHs. The first is the template search, which most people are familiar with, and that's where you directly compare the data against known GR waveforms using match filter technique. The second is a model-independent search. Now, this method does not look directly at the waveforms predicted by general relativity. Instead, it looks for, or it searches for an excess of power across your different detectors, your detector network. And it does all of this in the time frequency domain. So a cartoon of that is pictured to the left. So you can see we have different detector data streams, and we can look at them side by side in the time frequency domain. Now, the benefit to this type of search is that it allows us to potentially detect under-modeled or even unexpected signals. Now, on the bottom right is an example of what the algorithm what the algorithm saw for the first gravitational wave detection. So that would be the GW 150914, and you can see the two detector streams. And again, this is time and frequency, so you can see a clear signal in both detectors. Now, the main astrophysical reason that INBHs are interesting is because they're too massive to form directly from your typical stellar evolution. So on the left, I show the component masses for all of the 0102 LIGO detections shown in, and the component masses are shown in black, and the final mass of the remnant black hole is shown in red. Now the right plot shows the mass of the compact object, the y-axis, versus, or as a function of the mass of the progenitor star for different metallicities. And what we see is that no black holes are expected to form in the region from about 50 to 100 solar masses. And this is due to a process known as pair instability supernova. So in other words, if we find a component black hole in this, this region, it points to processes other than your typical stellar evolution. Now, during the previous two observing runs of advanced LIGO, LIGO Virgo, the loudest INBH trigger was detected with a false alarm rate of about 1 per 3 years, and that was found with the unmodeled search. In the time frequency plots below, again, so this is frequency and here's time, you can see that this signal, and the signal is shown, basically it's the red blob. Now, certainly you can see that this signal is less impressive than the one that was shown just a few slides ago. Nevertheless, if the signal were real, the total mass is estimated to be about 171 solar masses. That being said, main takeaway from this slide is that the event was not significant enough to claim an INBH detection. Now, in the case of a null detection, one important metric that we can calculate is our sensitive range. Now, on this plot, each circle represents a different pairing of component masses, M1 and M2. And for each pair, we can calculate the sensitive distance, in this case, in gigaparsecs. That is, this is a measure of how far out we can see a given source. And essentially, what we find is that in the INBH regime, we're most sensitive to the 100 plus 100 case. So 100 solar mass plus 100 solar mass system. Now, the numbers shown here from the 0102 INBH paper, it's linked on these slides. For 03, we expect about a 50% increase in our sensitive range. And finally, I'll leave this up as my final slide and just say that obviously it's been nearly 5 years now since the first detection. Certainly been an exciting time, and I think I can speak for all of LIGO Virgo that we are excited to show the new results from the 03 run. Thank you.
Thank you very much. Are there questions for Brendan? Just a reminder, please use the Q&A tool if you have a question. It's in the bottom right of your screen. I had a quick question. Is it possible that LIGO could observe a supermassive black hole merger?
No. Lisa should be able to see something with that high of a mass. In this case, LIGO Virgo should be able to see about maybe a total mass of 1,000, maybe a little bit higher for O3, but that hasn't been empirically tested yet. So so far the range is about to 1,000 total solar mass.
Okay, thank you. Any other? So a question, how do you get the direction to a black hole merger?
How do you get the direction to, I guess you mean where it's located in the sky. So that's a very detailed question. And in fact, I'll leave it up to my colleague Marek, who will discuss more on that topic in the very next talk.
All right, well, that's a great segue. So thank you for your talk. And Marek, if you would please share screen.
All right, can you see me? Can you hear me? Can you see my screen?
Yes, I can hear you. I can see your screen. Go ahead.
Perfect. So my name is Marek Szczepańczyk, and I will be talking today on behalf of LIGO and Virgo collaboration on the burst searches during the third observing run. So let me just get started. So LIGO Virgo was conducting the third observing run from April last year until the end of March this year. And so far we have published 2 observations from both are coming from April last year. LIGO Virgo is providing open public alerts for astronomers. And we had released 56 low latency gravitational wave triggers. So on the plot at the bottom, you can see how many events we had during the first observing run, during the second, and during the third that was ended very recently. So you can see a huge increase in number of potential gravitational wave triggers. And during this talk, I will focus on the low latency searches and the burst transients. So low latency analysis is a rapid identification of gravitational wave source and quick validation for astronomical follow-up. And we have 2 types of searches. First is a template base, when we know exactly what we are searching for, like binary black holes, binary neutron stars, and template independent, or we call them burst transients. And the typical examples are core collapse supernovae or strings, as well as some very unusual binaries, like very heavy or very eccentric binary black holes. We use, as Brennan said, introduced it in the previous presentation, coherent wave burst. This is an algorithm searching for gravitational waves for a very wide range of gravitational wave transients. It uses some very minimal assumptions of the signal. And coherent wave burst has detected the very first gravitational wave back in 2015, and the heaviest binary black hole so far back in 2017. And together with the template-based searches, it detects also many other gravitational waves. So you can see that this is a very powerful tool. So during O3, we were conducting several, I could call them flavors of the searches. We were searching for burst transients. These are signals when we don't know the morphology. Binary black holes focus. So for binary black holes up to around 100 solar masses, and intermediate mass black holes in the range between 100 and 100,000 solar masses. We use two search networks, namely Livingston-Hanford and Livingston-Hanford and Virgo. And in the table, you can see a summary of all the searches that we are conducting. That includes all the networks and source types. So, as I said at the beginning, LIGO Virgo is releasing public alerts, and you can find them on our GraceDB website. We had detected 57 gravitational wave candidates, and together with the template-based searches, coherent wavers detected 30 of them. During the first half of O3, we had 33 binary black hole candidates, and unfortunately we had 8 retractions. And during the second half of O3, we had 23 gravitational wave candidates, 22 are binaries, and we have 1 burst trigger. And this time we had 16 retraction. So let me give you an example of a public alert. The first one is from May 21st last year. This was identified by both template-based searches and coherent wavers. Its false alarm rate is 1 per 8 years. It's 97% chance that it's black hole, and the distance is pretty far, around 4 gigaparsecs. And the second example I want to show is a burst transient from January 14 this year. The false alarm rate is 1 per 26 years, and central frequency 64 hertz and duration 13 milliseconds. So it's very short and low frequency transient. There were a lot of follow-up observations, but nothing was found. Recently we have published a very interesting gravitational wave. You can find a preprint. This publication is submitted right now to PRD. It was detected by all pipelines that were running at the time online. Coherent waveburst provided a significance of this event 1 per 1,000 years. And what is interesting about this event is that it has very asymmetric masses of 30 and 8 solar masses. And also it provides a strong evidence that this event has higher order modes. So this is very exciting. And as a summary, let me say that LIGO Virgo has template-based searches and template-independent searches, and coherent waveburst is the prime tool to detect these triggers without knowing the morphology. Coherent waveburst has detected the very first gravitational wave and the heaviest binary system so far. We had released 56 low latency gravitational wave candidates during the last observing run. And please stay tuned to the next gravitational wave catalog that will provide a lot of information about the black holes and the population of these black holes. So thank you very much, and I will take your questions.
Thank you very much. Are there questions? I had a question for you first. Can you describe the process of refraction, how it's decided that that's necessary?
So The retraction happens sometimes very quickly, sometimes after a few days. First, the pipelines analyze data and they provide a trigger that when it goes below some thresholds, it is sent publicly. And then a committee meets up and we are discussing, is it a real event or not? So we have several experts coming from the pipeline experts to the characterizing of the detector experts. And they're checking if there is nothing strange in the data. For example, if there is an excess noise in the before the event, it might be some correlation. And we are also in touch with the people who are on the sites, who are checking if there is no any helicopter during the time of the event, any tornado, anything weird happening that can imitate the gravitational wave trigger. So when we collect all of this information and we see something strange, then the event is retracted. So there are many different reasons for the retractions, but mainly we want to make sure that what we provide to the public is reasonable.
Thank you. There's another question that was typed by Camille. It says, is there an ETA on the O3 catalog?
ETA, what is ETA?
Estimated time. What's the estimate on when the O3 catalog will be released?
That's a good question. And it should have been released a few months ago, but because of the COVID situation, everything is delayed. So I wanted to talk about this at this meeting, but unfortunately I cannot. I suspect maybe a month or two. It's hard for me to predict right now. Yeah, the COVID situation has delayed our publication plan quite a bit.
Okay, so we're going to move on. There's two more questions that you can take a look, that you can answer through the chat, but we're going to move on. So
Okay,
thank you very much again.
Thank you very much.
And our next speaker is Joseph Simon.
Oh, I'm sure. Like we just put these.
All right. Can you hear me and see my screen?
I can hear you and I can see you. Go ahead.
All right. Thank you so much. So my name is Joseph Simon, and I am a postdoc at the Jet Propulsion Lab. I'm going to be talking today about some recent results from the NanoGrav collaboration. So I'm going to take us to the other side of the gravitational wave spectrum and talk about pulsar timing arrays. So pulsar timing arrays are a galactic scale gravitational wave observatory, and we create this observatory by monitoring an array of millisecond pulsars, which are really accurate and stable clocks. Their spin rates are incredibly stable, and so we are able to search for correlated perturbations in the pulsar's time of rise that are caused by the stretching of space-time between the Earth and the pulsars. And so PTAs are sensitive to nanohertz frequency gravitational waves. And the primary source that's expected in this frequency band is a stochastic gravitational wave background that's coming from a cosmic population of supermassive binary black holes. So these are the most massive binary black hole systems in the universe. These are expected to form following major galaxy mergers, and the kind of cosmic population that we are sensitive to is roughly out to about a redshift of 2. So these are the most massive galaxies and black holes. And so their population then forms this stochastic background. So unlike LIGO searching for bursts, the signal that we are searching for here is actually embedded in our entire data stream. And so we need to model it with all of our noise at the same time. And so what we're looking for then are these correlated perturbations between each pulsar. And so the quadrupolar nature of the gravitational wave background means that the correlation between each pulsar is just dependent upon its angular separation in the sky. And so there's a specific prediction, it's called the Hellings and Downs curve, that that you can see here, and based on kind of where the pulsars are in the sky, their specific correlations between them are then predicted to lie on this curve. Now, the way that we search for a gravitational wave background is we search both in the auto correlation terms and in the cross correlation terms. But the auto terms are much louder, and they are expected to kind of be the first hints of what we would see, and then we would be able to confirm the source of the background by searching the spatial correlations in these cross correlation terms. And here I'm just showing a kind of cartoon of that correlation matrix, and you can see that the auto terms really dominate the power that we recover. So to be able to identify this this cross correlation term, we need to accumulate as many pulsar pairs as we can, so that we can distinguish this correlation pattern from other expected noises in the data set. All right, so we have recently completed our analysis of the 12.5-year data set. So this consists of 45 pulsars. And for the first time, we are seeing strong evidence of an uncorrelated common process. So this is just looking at those auto terms. So this is a common amplitude and a common spectral index for a power law model for the background, and it's present in all pulsars, and the evidence is incredibly strong. However, there's only marginal evidence on top of this for that specific quadrupolar spatial correlation that would be indicative of a background. So it is still unclear what the cause of this background, of this common process is. But these are some really exciting first steps, right? And one of the things that we've been testing, so in our previous 11-year analysis, we found that we needed to account for some uncertainty in where the solar system barycenter is. So the way that we reference all of our pulsar, all of the pulse times of is actually reference them to the inner frame of the solar system barycenter. So depending on which model of the solar system ephemeris we use, we get slightly different gravitational wave statistics. And so we've actually developed a new ephemeris modeling strategy that we call Bayes FM. And in our 11-year data set, when we incorporated that ephemeris uncertainty modeling scheme, we didn't find any evidence for a common process. But here, you can see that even when we incorporate that ephemeris uncertainty, we are still covering strong evidence for this process. One of the other things that we do is we have a statistic that just searches in the cross correlations. And so when we just do that, again, we find very marginal evidence for support of the Hellings and Downs quadrupolar term, and we can't quite distinguish that term from other spatially correlated processes. And so here I'm showing both the quadrupolar correlation in the blue and then just a flat monopole in the orange. And as you can see, we can't quite distinguish between these two at the moment. One of the other things that we're starting to do is we're starting to test the significance of these of our statistics, and so we are doing that by comparing against various null hypotheses, and we do that by breaking any true cross correlation in the data set. And as you can see, the p values here are intriguing, but are not not indicative that what we have here is a true signal and not just some noise. So with that, I'll say in summary that we are finding strong evidence for this uncorrelated common process, but it's still inconclusive what is causing it, and so stay tuned, because future data sets will show increasing evidence for these spatial correlations, if this truly is the first hints of the astrophysical background. And with that, I'll take some questions.
Thank you very much. Are there questions for Joseph? Camille says, forgive me, I'm not an expert in the terminology. Could you clarify what you're seeing in the pulsar timing that indicates there's a signal?
Sure. So, so what we are seeing is we are seeing basically we're seeing the same spectral power in each pulsar. So the same amplitude and spectral index of a red noise process in our pulsars, and while we can't distinguish what the spatial correlation of that process is, the fact that it is the same amplitude and spectral index in each pulsar could indicate that it's the kind of first hint of the stochastic background.
Thank you. All right, so our last talk was withdrawn, and so that makes this the end of the session. So thank you very much to all of the speakers in this session. This was very enjoyable, and I hope to see everyone around at the rest of the conference.